Hi, Jason. Good morning.
Oh, audio test.
Hello, Jason.
Hello, sir. Naririnig niyo ako?
Yes, perfect.
Okay. Perfect.
See, and we are going to start exactly 10 a.m. Let's wait
Apo.
for the others. Okay.
Sige, sir.
Okay, good morning. Hi, Jason. Uh, I think,
Hello.
hello. Good evening pala sa US. Okay. So we can start. I think Dr. Edita Jose, our Institute Director, is here in this Zoom webinar, but I don't see her audio. Okay. Probably when Ma'am Edits will be turning on yung kanyang audio, later na lang siguro ang kanyang brief speech. So for now, I think we can start our webinar series. Welcome to the 1UP Applied Mathematics webinar series. This is a regular webinar that we are conducting, and most of the speakers are from the University of the Philippines system, from Baguio down to Davao. Okay, so today we have Assistant Professor Mark Jayson Cortez from the UPLB Institute of Mathematical Sciences and Physics, and he is also a member of the UPLB Biomathematics team and the Quantitative Management and Decision Science Research Cluster. And also, Mark Jayson is currently a PhD student in the University of Houston. Houston. So he is currently in the US. Okay. So without further introduction, you can start, Jason.
Uh, yeah, hi. Good morning. Well, what I'll be talking about today is Bayesian inference for stochastic genetic models. Although I know that in the teasers it was Bayesian inference for biochemical reaction networks, but basically I'll be talking about the same thing. Yeah. So to start with the presentation, I would just like to point out the key points of my presentation. One would be I'd be talking about Bayesian inference for chemical reactions. So basically, be talking about what Bayesian inference is in the context of biochemical reaction networks. Secondly, I'll try to discuss what inference is for discretely observed processes. And finally, the main topic would be where I would be presenting the results of my research. That would be on the inference for multi-cell recordings. So just basic definitions and notions. When we say Bayesian inference, we basically talk about a task of quantifying knowledge about parameters of a certain model in light of the data and the prior information. So what we have is a trajectory of observations, and that we would be using this trajectory of observations in the context of chemical reaction networks and try to estimate the probability distribution, the posterior distribution of the parameters of the model. So this makes use of Bayes' theorem. So this is something we're very familiar with. So Bayes' theorem gives that the probability of, say, we have a model parameter theta and observation y obs. The probability of theta given the observations is equal to the probability of observations given theta, probability of theta divided by some normalizing constant probability of the observations. Now the green highlighted part here is called the posterior distribution. The yellow highlighted part is called the likelihood, and blue highlighted part is called the prior. So what we see here is the posterior being the probability of observing the parameter theta given the observation. The likelihood is the probability of having the observation given the parameter theta. And the prior simply is something that we know about the parameter. So this basically quantifies our belief or knowledge about the system or the parameters of the system. Just to frame the problem, so we could look at a chemical reaction network. So that would be composed of reactions, Ri, say R1 to Rv in this case, and a reaction is composed of two parts, the reactants and the product. So the reactant is basically composed of a linear combination, a formal linear combination of the species, or some sort of chemical species for instance. And then the product would also be a formal linear combination. So if we could just look at one of the lines here, so R1 is a linear combination. So on the right-hand side here, you will see the reactants. On the left-hand side, you will see the product. So in this context, each reaction, we associate a reaction constant, say theta 1 for reaction 1, theta 2, then up until theta q, or theta v for the last reaction. So basically what we do is to try to quantify or try to estimate the probability distribution of the given thetas. Suppose we are given a trajectory of molecular counts. So the data would be the molecular counts of each of the species at each reaction time. So basically what you would see here is a collection of trajectories that would be your data, and the parameters are the reaction constants associated to each reaction. Okay, so suppose you have complete information about your system. So that means you know exactly when a reaction occurs, at what time, and what are the molecular counts at each reaction time on some interval 0 to t. And that on the ith unit interval, you have ni reactions of type Kij. Then the likelihood becomes something like this. So you would notice this is something similar to an exponential, a product of exponential densities. I would no longer be discussing how we came up with that, but I would refer the listeners to a book by Wilkinson, which is published in 2006. So basically, the likelihood is a product of these functions. So, and now the hazard function h it simply describes the rate at which a reaction occurs. So you would see the h's in the likelihood right here. So you could think of the h's as the reaction rates. And then h0 is just the sum of all the reaction rates. That's how it looks like for the likelihood for a reaction. Okay, for a chemical reaction network. That's how it looks. That is how it looks like. Now, if you take rates which are mass action rate loss, mass action means that the rate at which the reaction occurs is proportional to the product of the reactants. That means you would have something that looks like this. For instance, if you have A plus B going to C as your reaction with some rate alpha, then the hazard associated with this reaction becomes H equal to alpha A times B, where A and B are the concentrations. Now, this is how a mass action rate looks like. Now, if we have mass action rate loss, then simple computations would show you that given the likelihood given earlier, and if you would take priors which are gamma distributed, then you would see that it is a conjugate prior. It means that a prior is conjugate if given the prior and given the likelihood, you would have a standard distribution as the posterior distribution. So a gamma distribution is a conjugate prior for the likelihood given earlier, this likelihood right here. And the posterior distribution of the parameters, theta, would also be a gamma distribution with the following shape and rate parameters. Okay, now what is the problem with that? Well, the thing is that for this to work, you would need to have complete information about the system. So that means you know exactly when a reaction occurs, what type of reaction occurred, and what is the molecular count at that specific time. Now, the problem is that given the state of science that we have at the moment, the state of technology that we have at the moment, it is impossible to track everything. So what usually happens is that we have discrete observations over time. So that means we take in intervals of observation. For instance, every minute, that's what usually happens. So for instance, on the left-hand side right here, you would see a complete trajectory, but what you would have is simply a subsample trajectory, which is observed every discrete time points. For instance, in this case, every minute. And what you would have is simply this information on the left-hand side, on the right-hand side rather. So you have x at time 0. X is the molecular count at time 0, x1, x2, up until x of t. So the initial task would be, well, now how then would we use the likelihood given earlier, or how would we redefine the likelihood so that we could do it just that we only have discrete information. So the initial task really is just to determine the number of reactions of each type which occurred at each unit subinterval. So because we have a latent process happening in between, the usual thing to do is just to simulate what happens in between. And for you to do that, you must first try to determine the number of reactions which happened and completed at each time interval. So the method was proposed in 2008 by Boyce. It's called the block updating method. The idea is that we use two blocks of Monte Carlo Markov chains. So a Monte Carlo Markov chain is a stochastic process wherein a Monte Carlo Markov chain in this case is that it is a stochastic process uh, whose whose equilibrium in the end would be the posterior distribution. Okay, so the idea is to use two blocks of Monte Carlo Markov chains. One block simulates the latent process, the unobserved process in between observations, and the other block simulates the parameters given the entire process. So a Monte Carlo Markov chain, one type of that is called the Metropolis-Hastings algorithm. One way to construct it, rather. The Monte Carlo, the Metropolis-Hastings algorithm proceeds in this manner, in these 4 steps. So basically, suppose you have a parameter theta. You would want to sample from the posterior distribution. So we generate a proposal sample from some proposal distribution Q, and then we accept or reject the proposal theta star, for instance, using this probability acceptance, which is simply a ratio of if you would notice, the ratio of the posterior distributions given earlier. Okay, and finally, we accept theta with probability alpha. I will no longer be detailing how this happens, but the idea is that because you do not know exactly how the posterior distribution looks like, you would want to sample from it. That to be able to sample from it, you make use of a method called Metropolis-Hastings, and this is how you do it. All right. So yeah, the basic idea is to simulate the latent process and use the simulated latent process in the sampling of the parameters. All right. So how do we do that? Well, basically, you would have to do it by simulating an inhomogeneous Poisson process in between observations. But well, you could do away with the inhomogeneous Poisson process, but you could instead just simulate a homogeneous Poisson process, and then just rescale the times. So basically, you would simulate a homogeneous Poisson process conditioned on the number of reactions. Okay, and then just rescale the time. So this one right here goes here, second one goes there. Now the time rescaling, I would no longer discuss, but it is, you could find it in the same book as I said earlier. It's Wilkinson, published in 2006. So just to recall what happened, you have a latent process which you do not know what exactly is, but what you know is that you could sample from, you could try to simulate that process. Now the thing is that you could always do a simplification of that. So what you could do, you do away with the inhomogeneous Poisson process, but instead just use as information the number of births and deaths happening in between observation times. So that would serve now as your data in the sampling of the parameters of the chemical reaction network. Okay. Then now the freshly sampled data, the freshly sampled parameter values would now be sent back to the Monte Carlo Markov chain sampling block, which now again just tries to sample again the number of births and deaths, which happened at time interval I+1. So this is some sort of a continuous improvement of the samples. So you have one block which simulates the number of reactions which supposed to have been completed at the time interval, and then send that information to the block which simulates now the sampling of the posterior distribution of the parameters. Now, the thing is that when you deal with biological models, there is large probability that you are dealing with a very large network. And that would make the inference process really tedious to do, because you would be having, say, for instance, if you have, say, 7 chemical reactions, that means you would be moving around in space in 7 dimensions, and it might make the inference process really difficult. Okay, so one remedy to this is to abridge the chemical reaction network. By that we mean try to simplify the chemical reaction network, do away with some parts of it, and then represent the simplified parts by delays. So you can think of it this way. So a chemical reaction may initiate at time, say, tau 1, but it has to go through, say, the process has to go through some more chemical reactions before you see the actual changes in the molecular count, like in this case. So the part which you no longer modeled, you could represent it by a delay. So you could think of it this way. So think of protein synthesis. Now, for protein synthesis to initiate, so you start with, say, transcription. But before you see the actual mature proteins after translation or post-translational modifications, it would take some time. So you no longer represent the in-between processes, but instead replace it by a delay. So that is one way to deal with it. Okay. So now, if you are dealing with delays in chemical reaction networks, the hazard or the reaction rates given earlier, it no longer works. So you must replace it with some sort of an effective reaction rate, which now we call the completion propensity. Now, the completion propensity, as you see right here, which is defined right here, is simply a convolution of the reaction hazard, H, as we defined earlier, with a measure. So the delay measure in this case. So for a completely observed system, the likelihood becomes this. So you will see that this is simply just replacing the hazard with the completion propensity F. So this is the same as replacing the hazard with the completion propensity F in this case, which is simply a convolution of the hazard with the delay distribution. Now, the thing is that this likelihood only works if you have complete information. So the idea now is for you to be able to approximate the completion propensity when you have discrete observations. The idea is to simply approximate the completion propensity with a function which is constant between observations. It starts with just averaging the completion propensity over the interval, say I to I plus 1, which is represented right here. Then interpolating the hazard between observations. So say for a fixed t, okay, so if this is your function f, or h rather, so before you integrate that, you could just subdivide that into parts, say from 0 to t, and then just replace this by linear interpolants. That is the idea. Okay. Now, this Bayesian inference for chemical reaction networks have been studied in detail in many papers, but a few have dealt with inference for multi-cell recordings. So the idea is that cells are different, and that we should be able to quantify the differences between cells. We should be able to say, by quantify, I mean, we should be able to describe how varied, say, the birth rates are across the cells in a population. So for the rest of the presentation, I'd be calling characteristics of an individual cell by parameters, and that the population level characteristics we would call the hyperparameters of the model. Okay, so for a generic multi-cell observation model, so suppose we have a birth-death process, say, so suppose you have a chemical species X, you have an influx of A, a rate A, and then a diffusion with rate parameter B. Now, suppose across the population, the distribution of A is described by a gamma distribution with parameters A alpha and B alpha. And then across the population, B is described by also a gamma distribution with parameters given as follows. Now, for every cell, you have A1 and B1, or AI and BI. The idea is that this is a generative model. So suppose you have a population level description, you have individual level parameters, and given the individual level parameters, you have observations, which are trajectories for the birth-death process. So the approach here, because what I have described earlier is just for single cell recordings. So the idea is that you sample from the posterior distribution of the birth and death parameters per individual. Using that information, try to simulate the latent process or in other words, try to determine the number of births and deaths which happens in between intervals or observations, and pass on this information to another sampling block which samples the population level hyperparameters. And given this one, send that information back to the block sampling, again, the parameters of each of the cells. That basically is the idea. Now, how do we visualize a birth process with fixed delay, or with delay? In this case, it's just fixed. So suppose the delays are sampled from, again, from a gamma distribution. So now a cell now is described by 3 parameters: the growth parameter, the death parameter, or the dilution parameter rather, and the delay, the fixed delay. So by fixed delay, we mean that every time, suppose, so again, let's go back to the chemical reaction here. So A, B right here, and suppose the birth reactions have delays in it. So every time a birth reaction occurs in this case, you have to wait a fixed amount of time before you see actual changes in molecular count. So it's no longer instantaneous. Okay, so the completion propensity looks like this right here. So what happens is that the fixed delays would mean that you would have a measure, or the probability distribution, or the distribution now for the delays is just a direct pointless measure centered at some fixed point dn. Now, if you would go back to the approximation given earlier, so we are averaging the propensity on the interval I to I plus 1. Since we have constants A as our birth reaction or birth parameter, now this nu right here is just a direct pointless measure. Now with that, everything just simplifies to something which looks like this. An times some constant Pni, or where the constant is just simply either 0 or the minimum between 1 and I plus 1 minus Tn. Okay, now I'll now be presenting some results of our research. So if you have a population distribution, so again, we are talking about fixed birth delays here. Birth of process, you have multiple observations. Now, suppose you have the data. The data looks like this, for instance. So you have this set of trajectories. You have the birth reactions, birth rates, birth parameters A, B, and delay D, which are sampled from, say, gamma distributions each. So A is gamma 25.5, so the mean is 5. B is from gamma 210, so the mean is 0.2. And then D is from gamma 3.6, 0.6, so the mean is 6 minutes. Now, the only thing that we know is this set of trajectories. So what we were able to do is we were able to describe the population distribution and the individual level distribution of the parameters accurately. So if you would see, look here at the right-hand side, above here you would see the population distribution. The true density is given by the orange curves, and the result of our model would be from the blue one. You notice that we have distributions, we have estimates of the true distribution, which kind of have means which are almost equal to the mean of the true distribution. It's just that in our case, say in the case of, say, the birth parameter A, we have a flatter distribution, which is expected because we only have a finite number of observations, a finite sample from the true distribution. But still, we were able to accurately estimate the mean, in this case, which are given by the markers right here. And that is especially true with the delay. And that on the individual level, you would see here at the bottom, these are the normalized means of the individual cell growth rates. So you would see that our estimates are within, say, 0.1 or 10%, within 10% of the original value. And that is also true for the expected delays, which you would see right here. Now, we tried specifying the data. So that means that we did not use data with fixed delays, but instead data with distributed delay. So our findings are that the parameters are underestimated when the generative model is specified. So that means that the data from the model from which our data was from is different from the data from which we generated the hierarchical model given earlier. So we have underestimations of the parameters, as you would notice here, specifically for the delays. For the birth parameter A, we kind of got the shape of the true distribution, the true density. But if you would go to the mean delay distribution, it is underestimated. Okay, and that translates to the underestimations also in the individual level. Now you would see here it's about just around 0.5%, around half of the original delay. But we tried to simulate trajectories given our estimations. And we noticed that here on the left-hand side, we still were able to represent the data using the misspecified values. This is a caution to using, this now tells us that we might still be able to recover the data or to get a semblance of the data given the underestimated values, but that is under the assumption that we have fixed delays. So it kind of cautions us about using fixed delays to represent distributed delays. So the result is kind of important in the sense that it tells us that there might be effects on the estimations of our parameters when we represent distributed delays with fixed delays. This is what this is showing us. Now, if we would go to a model with distributed delay, so the idea now is that each cell is represented by 4 parameters. You have the birth parameter A, the death parameter B, and the delay parameters alpha and beta. So the delays now are sampled from a gamma distribution. So for instance, for cell number 1, the delay D is sampled from a gamma with parameters alpha 1 and beta 1. And every time a birth reaction occurs, we are still talking about a reaction of this form, A, B, and then you have birth delays tau. So every time a birth reaction occurs, there is a delay which is sampled from a gamma distribution with parameter alpha 1 and beta 1. And this is how we visualize the generative model. So if each of the A, B, alpha, and beta are sampled from some population distribution, which are all gamma distributed. Now, the completion propensity, now remember the completion propensity is the effective rate of reaction, now takes the form AN, the integral from I to I plus 1 of this expression right here, dt. Now that expression right there is simply the gamma CDF. So this simply is the integral of the gamma CDF, the community distribution function. For prior distributions, we set gamma priors for all the parameters. And to describe the hyperparameters, we use as hyperprior distributions what we call the maximum data information prior, MDIP. This is a prior derived by taking the distance, by maximizing the distance, the Kullback-Leibler divergence between the density of the observation. In this case, these are the hyperparameters, the distance between that density and the prior distribution. What you would have after that maximization is called the MDIP. Okay. Now, as example, on the left-hand side, you would see data generated by taking A, B, alpha, and beta from the following gamma distributions. So we simulate a trajectory or a set of trajectories from values taken from these distributions. Now, what you would see on the left-hand side are results of our estimations, our Bayesian inference. Still, the true density is given by the orange density, and the result of our model is given by the blue. Okay. you would notice that we have accurate estimates for the growth rates A, but for the the mean delays, we kind of have overestimations, but majority of our samples are at the lower end of the density. So still, the growth rate and mean delay times are mostly accurately estimated, even with uninformative priors. So when we say uninformative priors, this is a prior which does not give you much information about the distribution of your parameters. So at the bottom of this panel, you will see the normalized values of the expected birth rates, and you will see that the values are well within a small interval from the true values, okay? But we are having a hard time making accurate estimations for the expected delays, because as you will see here, these four right here are quite large, like around 1.5 to 2 times the original values. But most of the individual level estimates are well within some good interval from the true values. And also, one finding is that correlations among individual level parameters are also reflected in inferred values. So here, what we have is a model misspecification, in the sense that we no longer generated our data using a model which looks like this, but instead we changed the parameter generation in this manner. So we generated delays which are positively correlated with birth rates. So what we did is just to represent the first parameter alpha by a linear function, say 0.2 an plus some epsilon, which is coming from a normal distribution, and just fix the betas. Now, on the left-hand side, you will see the pairwise comparison of the true values and the predicted values from our model. The predicted values are given by the red dots, and the true values are given by the blue ones. We assume that the death rates are known, so we are no longer inferring them, because based on some experiments, the death rates are kind of easy to estimate. So we no longer do that. So we just assume that they are known. And then you would notice that, so our interest here is really at the middle panel. Clearly, for the blue ones, you see a clear positive correlation between the delay and the birth rate A. But the results of our model show that this correlation is represented accurately for small values of A. But the larger the A becomes, the less accurate the predictions become, as you would notice here. So the largest error occurred at the combinations of high growth rate and high mean delays, as you would see on this part right here. And also there is a noticeable shrinkage of growth rates towards the mean of the distribution. Shrinkage means that the values are pulled towards the mean of the distribution, which is around 35 in this case. And that is characteristic of hierarchical modeling. That shrinkage it's quite expected in this case. This is inherent in the modeling process that we used. Okay, now everything that I've shown you so far are results on simulated data. But on the next few slides, I'll be presenting results on experimental data. So this data was used in a study by Choi in 2019. They developed a Bayesian inference algorithm for the same birth process, but for a single cell observation. So the data were from an experiment on YFP synthesis. This is a protein in E. coli using time-lapse fluorescence spectroscopy experiments. And the results of the simulation in one of the experiments show that the estimated production rate A is around 35, and the mean delay is around 6.6 minutes. And they have data for 39 cells. So I mentioned about this being a study on single cell observations. So they assumed that all the cells, all the observations are for the same cells. So that is their assumption. And they difference between the cells. That's the assumption that they made. Um, this now are the results of our model. So the individual level estimates are similar to results from the single cell inference. So this is above, you would see our estimates for the population distribution of the birth rates and mean delays. Uh, and below you would see the individual level estimates. And the blue line here represents the mean of the posterior means, which is simply the mean of all the estimates given right here. So this is given by the blue line. And the red line is given, it gives you the single cell estimate. Okay, so you would see here that at the individual level, our estimates are similar to the results in the single cell inference, which kind of validates our approach, both for the mean growth rates A and the mean delays right here. Okay, it's just that in our case, the mean here is above the single cell estimate, which is 7.4 for our approach and 6.6 for the previous study. And these values are similar to the reported time maturation of YFP variant Venus in E. coli, which is around 7 plus or minus 2.5 minutes. This has been reported in some experiments on lab experiments. So there, here are my references. And special thanks to the following people who have been helping me in this project for the past few months. Dr. Kresho Yosich from the University of Houston, Dr. Jae Kim from KAIST in Korea, and then Dr. Bosong Choi from Korea University, Sejong Campus. Thank you so much for listening, and I'm now ready for your questions.
Okay, thank you, Jayson, for that wonderful talk. Before we continue with the question and answer, may I request those people in this Zoom webinar to open their videos, especially you, Jayson.
Hello.
Hello. How's the situation there in Houston?
It's kind of grim.
Okay.
Hindi ko alam. Definitely it's much worse than the Philippines, although we are still COVID-free here at home. But yeah, I haven't been out for the past few months. So, pumuti na ako.
Talaga? Okay. Yep. Okay. Sige. Okay. Our institute director is also here. Probably I can start the question. There's a question.
Hi, Jayson.
So there's a question by Jonathan. Jonathan, you want to ask your question or basahin ko na lang?
Kahit basahin mo na lang.
Okay, nahihiya si Jonathan. Okay, sabi ni Jonathan, the question here is, in the experimental data, do you estimate the parameters of the model? What methods did you use in estimating the parameters?
Okay. I-share ko lang yung screen ko ulit. Yeah. So let's just go back to that slide. Yeah. Yeah. So the idea is that we try to, the estimation is inherent in the process. So what we do is to try to estimate the probability distribution of the parameters, in this case, A and B for each cell. So because in the previous studies, the basic problem is that we do not have a complete information about each of the trajectories, and we only have information about discrete time points in space. So the idea is, instead of using the likelihood given at the first part of the presentation, you try to simulate what happens in between. And then using this simulated process, you could now use the information given earlier. But what I've used here in the research is a simplification of that process. So the idea is that you would go back to the Bayes theorem. So the end product is this right here. So the end product is a probability distribution. So the process is, instead of having a functional form for the probability distribution, what you have is a set of samples from the probability distribution. So what I presented in the last parts of the slides are just histograms of the samples from the probability distribution. Okay, so the sampling process is done in this manner. It's given by this algorithm right here. So you try to initialize, say, for instance, theta, and that will be your first sample. The second sample would be coming from some proposal distribution. This is usually the normal distribution centered at the previous sample. Now you accept or reject that sample, the proposed sample, using this criteria, using probability alpha. Now this is just a minimum of 1, and the ratio of the posterior distributions of theta star, which is the proposed sample, and the previous sample theta. And then at the end, you would have a Markov chain, say theta 1, theta 2, and theta upper nu. And that would be your posterior distribution. So that is the idea. So instead of a functional form, we have a set of samples from the probability distribution. That is how you try to estimate. So at the end, if you want a single point estimate of the parameter, just take the mean of the posterior distribution, and because you have a probability distribution, say for A, yung error estimate is inherent in the process. So you could say you would have a 95%, say, HDI, or high density interval. So you could say A is equal to, say, 0.5 with 95%, with this 95% confidence interval. So everything is that measure of the error is inherent in the process.
Jayson?
Yes, sir.
Yung theta ay set of parameters or set of data points? Sorry, hindi ko na-gets.
Yung theta ay set of parameters.
Okay, gets that.
Yeah. So the idea is that we want to quantify, or we want to estimate the posterior distribution, or the distribution, probability distribution of the parameter theta, given just the trajectory of observations.
Okay.
So it's akin to parameter estimation with continuous observations, but this time we don't have that. But when we have our discrete time points in space.
Is it similar to maximizing your likelihood function?
It's different in the sense that you are not taking the maximum likelihood estimate, or the MLE, for the parameter, but instead you are, if you want point estimates, you want to maximize the posterior distribution. So more properly, you would want to take the mode of the posterior distribution, but because you have a set of samples from the posterior distribution, what's more proper is to just take the mean.
Ihabol ko lang yung isa ko pang question, Jayson. Sorry.
Yes, sir.
Yung sinabi mo na yung latent process mo, meron siyang Markov chain. Nag-consider ka ng martingale condition of this process?
No, sir. Ganito yung mangyayari. So, bale, meron kang, say, observations, say, at I and I plus 1. So you have, say, xi here and xi plus 1 right there. So ang idea ay, try to simulate what happened in between. So itong simulation na ito, for the long process, yung hindi simplified process ay, what you would do is to try to simulate it using an inhomogeneous Poisson process. But instead of inhomogeneous Poisson process, which is more complicated to do, simulate a homogeneous Poisson process in between, conditioned on the number of reactions. So your number of reactions ay, again, meron siyang sampling process. So it's similar to maximizing the likelihood. So Poisson A times Poisson B, xii plus 1 over 2, just try to maximize that. So combinations A and B. and that conditioned on A and B, meron kang homogeneous Poisson process. So that means magiging lang siyang uniformly sampled between I and I plus 1. Take uniform samples ng time, tapos rescale the time. So that would be equivalent to an homogeneous Poisson process. Yung rescaling ng time niya ay dependent on the hazards at the time of reactions. Yung book ay by Wilkinson, 2006. Meron siyang complete complete discussion kung paano ito ginagawa.
Thank you.
Thank you.
Okay. Next question. Do you have question, Ma'am Edits?
Ako talaga. Sabi ni Jomar, magtanong daw ako kasi CRN. Pero wala, hindi ganyan yung ginagawa namin. Ano, Jayson?
Opo.
So, pero,
Ano siya?
I mean, yung CRN theory kasi, it's a parameterless theory. So, yun nga yung advantage ng chemical reaction network theory. You can conclude somehow about the behavior of the system without considering the parameters. Pero yung I think ang ginamitan lang ng CRN parang sample system in terms of CRN, tapos kasi may mga parameters kang hahanapin. So basically parameter estimation yung study, hindi siya talaga chemical reaction network theory. So ano naman ang nagamit mo dun sa ating CRNT? So, parang wala. How would you connect? How would you connect the theory itself, what you are doing?
Yung reaction hazards na kinonsider namin dito, ma'am, ay mass action.
Yun lang. Yun lang.
Kasi maganda dun sa mass action hazards dito ay yung form noong posterior distributions, marami sa kanila ay known standard distributions, gamma distributed sila.
So, hindi pwede yung power law kinetics natin.
Pwede rin naman, ma'am. Pwede ang Hill functions, pwede rin ang Michaelis-Menten kinetics, power law kinetics. It's just that sa kasong ito ay madali siya dahil mass action yung
mass action. So, we know the may form. Okay. So, anyway, okay. Anyway, so wala akong masabi kasi medyo iba yung I mean yung focus ng CRNT 'di ba? Iba siya.
Ito, ma'am, more of siya computational in the sense that ina-estimate namin yung posterior distribution instead of analyzing yung network itself. So mas siya mas geared siya towards application sa estimation ng mga parameters. Tsaka gusto namin talaga ma-describe yung population distribution sa mga cells.
Yes. Okay. So is this part of your dissertation? Ito na yung dissertation. Okay. So Hopefully. So, kaano mo pala dyan si Dr.
Jay.
Si Dr. J.
Yes,
so ang applications nyo ay kasi ang alam ko ang ginagawa niya ay more of circadian clocks, di ba?
Yes, ma'am. Pero isa sa mga sa mga collaborators namin dito.
Okay. Okay, kasi 1 year nga daw siya nag-postdoc dyan. Kaya
dito siya, ma'am, ngayon sa US.
Okay. Anyway.
1 year yata siya dito.
Wow. Anyway. Sige, good luck na lang. So, ano ba yan? First paper or towards your
hopefully first paper, ma'am, in 2 months.
Okay. Sige. So, good luck. Good luck. Yun lang good luck. Maitatanong din daw si Gerald.
Yes, sir.
Jayson.
Sir.
Rep lang kayo, hindi ko maintindihan Tatanong ko lang yung di ba pang sa molecular, yung data mo ay molecular count, tama?
Yes, sir. Opo.
So, kung pwede mo rin bang i-apply ito sa macro level, for example, population ng
Yes, sir. This is dynamics epidemiology. Actually, sir, tingin ko nga ano siya eh. Ay, sir, tapos na po ba yung question niya? Sorry.
Sige, yun lang.
Tingin ko nga, sir, mas ano siya eh, mas applicable siya in the sense that hindi siya continuous. So, parang yung mga tao, hindi naman talaga continuous. But ang kinukuha mo yung ang data mo talaga ay discrete. So, pwede mong isipin na yung number ay yung molecular count ay yung bilang ng tao. So, ganun.
Pero parang ano lang siya, no? Parang ka nag-interpolate in between observations, no?
Ano, sir? Yung initial na method ay ganun po, sir. Ano siya, parang in between observations, nagsasimulate pa siya. Pero yung ginawa namin ay hindi na. Basta alamin mo lang yung nangyari. Alamin mo lang yung bilang in between. Tapos sapat na yun.
Pwede mo ba siyang gamitin na forecasting technique?
Anong sensor? Paanong?
Sense na yun, so kunyari, population, yung trajectory ng population. Given na hindi lang individual population, for example, kunyari, may dalawang nag-interact na species, mapipredict mo kaya yung trajectory ng
most likely, sir. Kasi yung original paper nito ay nag-work sa itong paper by Boyce, 2008. Nag-work ito sa isang Lotka-Volterra model. So, meron sila doon mas maraming chemical reactions. So, bale, doon talaga nila in-apply ito. So, I guess the answer is yes.
Thank you, Jayson.
Yes, sir.
Good luck. Sana matapos ka na. Ingat
Sana
din
na.
dyan. Ang daming dyan, ang daming may COVID.
Literally, sir, hindi pa ako lumalabas ng 3 months. Literal.
So, pa-deliver kayo.
Deliver. Sinil lang ang lumalabas sa amin.
Sarado rin ang university?
Bukas, sir. Pero kailangan ng special pass. Merong ganun.
Hindi naman kayo nire-require pumunta.
Hindi, sir.
Hindi naman. Anyway, tapos na ako kayo. Thank you. Thank you, Jayson.
Okay. I-mute lang muna kita, Gerald. Ayan. Ang ganda ng background ni Gerald. Parang gusto ko mag-swimming with the dolphins. Joke. Tawag dito. Currently, nag-message sa akin si Ma'am Kayen, shout out, at si Sir Au. Nanonood sila sa YouTube. Okay, nasa YouTube. Actually, masarap manood sa YouTube kaysa nasa Zoom. Kasi, anyway, may question pala ako, Jayson. Related din with Gerald. Previously, I encountered methods na like that. Although not really on the molecular level, more on the population level, especially in infectious diseases. Lalo na pag may mga seasonality. Yung mga from one point to another, di ba may changes. Tapos minsan may delay. Ang ginagamit nila, what they're using is splines. And later on, i-generalize. Have you encountered or what although syempre splines are mostly deterministic, but have you encountered those kind of methods, and ano yung possible na advantage nung looking at that stochasticity rather than with those splines?
Sir, yung dinidescribe mo, sir, ay in between observations, nagkakawa sila ng splines. Then, ginagamit nila yun to estimate. Well,
yung mga parameters.
basically, sir, basically, sir, I think that is more of assuming that you have continuous data. And so I mean, sir, everything is discrete. The data is discrete. So pati yung molecular counts are discrete. But I'm not really sure whether that would be more beneficial to use. But no, I'm not really sure how to answer that question, sir. But yeah, we also make use of splines in our case, but it is only for approximating the hazard functions in between observations. So, but I guess it's kind of the same idea, but the use of splines in our case is just for the estimation of the hazards instead of estimating the data points, using the splines to estimate the data points in between. Was I able to answer the question, sir?
Yeah. I have a follow-up question. Yeah, of course, most of the distributions that you used when I was watching your presentation, mostly gamma. So pag gamma, mostly two parameter, you can fit many situations doon, no?
Yes, sir.
Many scenarios. Have you like also sort of estimated the pag-blow up ng errors? Let's say kapag, especially when looking at the delays, kasi pag molecular, iba-iba talaga yung dynamics and the delays could be very different. If you have encountered certain scenarios na iba-iba talaga yung dynamics individually of the molecules, then later on through time lalaki din yung agwat. What is parang calculations nyo on the possible error through time, or robust ba yung method for any scenarios?
Yeah. So far, sir, we've only tested on model specifications twice. One is when I guess, sir, ang pinupunto mo ay, so because you represented everything in terms of, say, gamma distribution, or what then are the possible effects in the long run? Is that the question, sir? We haven't really tested on that. So far, what we have is just try to compare the posterior distributions that we have to the two distributions. But it is really a valid comment. Yeah. And so far, we've been really having trouble with estimating the mean delays, especially because we are working with uninformative priors. So that means we are assuming that we don't know something, or we know very little about the delays. So, yes, sir. I'm not really sure. I think that's tangent to the question, but I'm not really sure whether I was able to answer everything.
Yeah. Naisip ko lang because definitely in molecular dynamics, you're also talking through time. And possibly, I mean, baka, especially if there are molecules that medyo divergent in dynamics. But anyway, that could be very rare, or I don't know.
Yeah. Usually, sir, sa mga papers sa mga ganito, yung mga ginagamit nilang time observations is around 20 to 40 minutes lamang. So I'm not really sure whether that would be a concern in the end.
Okay. Yep. Okay. Yep. Do you have other questions? Yung nandito sa Zoom. Let me check few seconds if there are some questions in the Facebook. Okay. Facebook, wala naman. Mostly the comments are in Facebook kasi naka-child lock yung ating comments sa YouTube para hindi PG, IRR 18 tayo, baka may mag-comment na. Naka-automatic siya for that. So currently, none. For those people who are watching or who will watch, our video, Jayson's presentation is recorded in our 1UP YouTube channel. So you can watch again and absorb Jayson's talk today. So I think none. And so para hindi na rin mahaba yung ating webinar, let's ask our IMSP Director, Edita Jose, to share some thoughts and closing remarks.
Impromptu na naman. Okay, so thank you again, Sir Jomar, and of course Assistant Professor Cortez for his nice talk. And I think this is the what the fourth? Is it the fourth or the third?
The third.
The third. I missed the second. Who is the second?
Fourth.
Fourth na?
The first one is Jeric.
Jerry.
The second one is
Yeah.
MS student in Diliman, and then
And
now si Z, and then Jayson.
Okay, so this is the fourth. And we just continue this webinar, and I think everyone is knowing what everyone is doing. So kasi nga we want to build this applied math community in the Philippines, and so we know who's doing what. So I commend, of course, the initiator of this of this webinar, Jomar, and I'm looking forward for more talks. Ano ba to? Weekly ba? No.
Almost weekly.
Almost weekly. So let us encourage more participants and viewers in our YouTube account. May YouTube account na ba tayo? Dat pala may YouTube
Yes,
account tayo, no?
We have YouTube account, and we have I think 200 subscribers already, and many actually after this maraming nagwa-watch kasi
okay.
siya forever.
So I hope more to come, hindi lang local kundi international viewers we can advertise, no? And we hope for collaboration within. Of course, maganda yung ASEAN neighbors natin. We can collaborate with them also. Dahil medyo, I think, accepted na ngayon yung hindi physical collaboration, but through online. So again, thank you very much to our speaker, okay, Assistant Prof. Cortez, and to our host, Dr. Rabahante. So see you again next time. Thank you so much.
Okay, before we go, plug in lang. We have already actually scheduled yung mga susunod. We have actually saktong-sakto. The next is also, I think, about CRNT. The talk will be Brian Hernandez. He's the representative from UP Diliman. Tentatively, but ito na yung bigay na schedule, July 11. And then there will be others from UP Mindanao, may nakaschedule na. And then i-announce ko na Edu, nakapila ka na. Umuon si Edu sa akin. Edu Hatulan from Taiwan, and then Ruday na. So marami nang nakapila, and which is very good kasi I think people are excited to share their different researches, especially related to applied mathematics, and Aja fighting. Okay, so thank you very much. This is another one UP Applied Mathematics webinar, and I hope everyone is safe, stay safe, and stay healthy. Good morning, good evening there, Jayson. Bye-bye.
Good morning.
Bye-bye.
Thanks so much.
Bye.
Thank you, Jayson.
Thank you.
Long hair.
Longest it's ever been.
Say hi to Jeric and Neil.
Yeah.
Nasaan sila? Andyan sila?
Nasa sir. Nasa kanya-kanyang workstation nila.
Okay. Okay, sige.
Okay.
Okay, sige. Bye-bye. Bye-bye.
Bye-bye.
Hi, Jayson. Bye-bye.
Ma'am, bye-bye. Ingat, ma'am.
Ingat.
Okay, I'll end the meeting. Bye-bye.
Bye-bye.